So this session will be presented in representation of our institution, the CSIC, by Ana Castro, who is the Vice President for Innovation and Transfer of Knowledge. So I hand over to Ana, please.
Muchas gracias, Rebecca, y buenos días a todos. Good morning and welcome to this conference. I would also like to start by thanking Rebecca and your team for organizing this session and proposing this initiative. Thank you very much. On behalf of our president, Eloisa del Pino, I would like to welcome our distinguished guest, Professor Joanna Haigh. Thank you to be with us today and welcome to CSIC. The topic of the conference is the science of climate change and represents a unique opportunity for discussion and a time when we can take advantage to update about lessons that we have learned. And because providing a space for debate like this in the field is necessary, especially now where access to scientific information and dissemination of knowledge is so relevant and undergoing so many changes and challenges, especially when we are talking about issues with a global impact. At this point, let me mention the COVID-19 pandemic and try to draw parallel similarities between the two. I would like to suggest a certain relationship between the health crisis and the climate emergency we are facing, because in my view, the pandemic we are fighting and the climate change is important element in common. Both phenomena highlight something very simple, that whatever our difference, we are sharing this planet. Both are crises that affect us all. The pandemic does not discriminate between people or countries. In the same way, climate change impacts on the future of the planet. I'm sure that today's conference will make a significant contribution to the global conversation needed to address these challenges. So enjoy and thank you very much.
Thank you very much for your words, Ana. It's a pleasure and it's an encouragement for us to have the support of the SIG in this kind of event. So, well, today's talk is called the Science of Climate Change. And climate change or global warming is a cause for deep concern for millions of people around the globe. And we are concerned for a reason. We are concerned because we don't really know if this planet is going to be a livable place in maybe 50 years or so. And we're concerned because we are directly experiencing extreme weather phenomena that put lives at risk, like floods or hurricanes. So we know it's there. So we get constant information about climate change, but of course there's such a wealth of information that we also get misinformation and sometimes disinformation, no? That's deliberate false information. And it's difficult to tell for the non-expert, what sources of information are valid, have a support in science. And it's really important that we can tell, because if we are going to face the challenge, it's not just knowledge, we have to take decided action. So that's when we thought of inviting Professor Joanna Haigh to give this talk. Joanna has a really broad curriculum. I'm going to very briefly summarize some of her positions and activities. She is Emeritus Professor of the Atmospheric Physics Department in Imperial College, London. She was formerly the co-director of the Grantham Institute on Climate Change and head of the very prestigious Physics Department in Imperial College. She has published widely on radiative transfer, and she has devoted a large part of her own research to describe the impact of solar activity on the climate. And she has also had crucial contributions in the international scientific community. She's been part of the Intergovernmental Panel on Climate Change, the US National Academies of Science, and the European Space Agency. She's a fellow of the Royal Society, an honorary fellow of Somerville College in Oxford, and also of the Royal Meteorological Society, of which she was president in the past. So Joanna has an impressive curriculum on climate science, and we are sure that she will illuminate us on this subject. When I first wrote to her, it was the year 2019. Her talk was initially scheduled for almost exactly 2 years ago, October 2020. The pandemic changed our lives. The curricula were suspended, and we are really happy that we finally managed to bring her over to Spain to communicate with us. In these 2 years, we have, for instance, experienced the hottest summer in record. So we believe that her talk is not just timely, it is urgent. So we are, thank you very much for coming. We are pleased to have you here. It's an honor. I hope the young people and, well, everybody can participate after the talk and with comments and questions. So please, Anna. So please, Joanna.
Well, thank you very much, Rebecca, for those kind words, and also to you and to Anna for inviting me to talk at CSIC, which is really a great honour. And in this room, it's amazing, beautiful, much nicer than many of the lecture theatres that I talk in. So it's a pleasure to be here. Thank you very much. So I'm going to talk about the science of climate change. I hope to talk about it very broadly, about what's happening, why it's happening, and what we can do about it. But of course, that's rather a large scheme of things, so I'm going to be going rather quickly through some things, and I hope you'll be able to understand what I'm saying. If not, wave your hand and say, hang on a minute, stop, what was that? I won't mind at all. So let's see if I can get this thing working. Oh, point it over there. No, gone twice. Right, where shall I stand best? Over this side? Yeah. No. Yes. Okay. Well, this is of course is the background to the whole thing about what was called global warming and now more generally called climate change. And it's a graph showing the global average temperature of the Earth over a period since 1850 to the present, and it's been reconstructed in different ways by different people, and you can see that all the coloured curves are fairly consistent. And they're showing, can you see that pointer? Yes, a gradual warming over that period. Now, of course, it's going wiggle, 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 and it's not a smooth warming, but it is going up. The last 7 years have been the warmest on record, and each decade of the last century has been warmer than the last. So you can see it's definitely happening. This is observational records. Now we're getting into a bit of the science, and to understand about the surface temperature of the Earth, we have to understand the energy budget of the Earth. And what this plot is showing is the incoming solar radiation, so that's all the energy that's driving the climate system. There's nothing coming from anywhere else, tiny little bit from underground, but nothing really. So all the energy is coming from the sun, and it's mixing around in this complex system here, and then heat radiation is going back out to space. And on a global and annual average, and if there's no climate change, the amount of solar energy coming in will balance the amount of heat energy going out, and that's an equilibrium. But you see, in terms of what's affecting the surface temperature, there's all sorts of things going on here. Of this incoming solar radiation, about a half gets through to the surface and warms the surface. And then the surface gets hot, and it emits heat radiation, or infrared radiation, outwards. But only 90% of that is absorbed in the atmosphere. Only 10% gets through, and then the atmosphere gets warm, and that emits heat in both directions, but particularly back down to the surface. So the surface is warmer than it would be were the atmosphere not here. And that's what's become known as the greenhouse effect. So the surface is warmer because of the gases in the atmosphere, have a different absorption property for solar radiation and infrared radiation. So anything that affects any of these streams will affect the surface temperature. So you could, if you change the surface reflectivity of the Earth, which you can do in many ways, one by different agricultural practices or chopping down trees. Or if you change the composition of the atmosphere with the greenhouse gases, or the composition of the atmosphere with particulates, with dust and smoke and things, they will affect the radiation getting reflected to space. So we need to understand the whole of this complex system to know what the surface temperature of the Earth is doing. But at first I'm going to concentrate on the greenhouse gases. And if we look at the gases in the atmosphere, here they are. Most common is nitrogen, nearly 80%, and then oxygen is most of the rest. And then we go down with these ones until we get to carbon dioxide, is about 0.04%, or 4 molecules in every 10,000. And then water vapor is very important, it's very variable, so 0 to 4%. But if we look and see the greenhouse gases, nitrogen and oxygen do nothing. They're just sitting there and the radiation's coming right through in both directions. But carbon dioxide and water vapor are both strong greenhouse gases, and they're the ones that are causing the surface to be warmer. And if we look at that in more detail, now this looks a bit techie, but I hope you'll bear with me. This is a spectrum. Now, you know about spectra because you've done, if you look at the light, it can be divided up into different colours, the colours of the rainbow. This is actually the same thing, but it's actually in the infrared radiation. And again, there's lots of different wavelengths. And what the red curve here represents the spectrum of radiation coming out of the surface. And the wiggly line is observations of the radiation that gets out to space. So the difference between the red curve and the wiggly curve is the radiation that's getting absorbed in the atmosphere and causing the warming. And you'll see some of the gases identified here as to where they're important. And I can show that in more detail in the next slide. And what this is, it's the difference between the red curve and the speckledy curve, but the influence of the different gases. Now you'll see all these values are negative because less radiation gets out when those gases come into the atmosphere. So that means there's more trapped heat, and that's warming. And the different gases are down here, and you see the red one is water vapor, and that has the largest effect. So the water vapor in the atmosphere is responsible for the Earth being about 30 degrees warmer than it would be were there no atmosphere. So we have this lovely planet that we live in and all the plants grow, and we need the greenhouse effect. It's a lovely natural effect. It's when it gets enhanced that we get problems. So water vapor is the most important one, but then you see CO2 here in this pale blue colour is the next most important one, 25 watts per square metre trapping. And you can see it's, I'm sure the physicists here will be able to tell me why, but I've forgotten. Its absorption spectrum is just particularly strong where water vapor isn't absorbing, which of course has a lot of important effects. So water vapor is absorbing in the far infrared and in the near infrared, but in this gap here where water vapor happens to be inactive, there's a big absorption by CO2. Now, if you put more water vapor into the atmosphere, only a limited amount of that can stay there because it condenses out against clouds and rain. So it's sort of constrained, the amount of water vapor that you can put into the atmosphere. But you can put as much CO2 as you want into the atmosphere and the concentration will go up and up and up, and that's what's happening. And this absorption peak will get deeper and deeper. So let's see what CO2's been doing. These are measurements from Hawaii, so that's a nice clean air in the middle of the Pacific Ocean. It's representative of what's happening across the globe, of carbon dioxide over the last 60 years. And you can see it's just going up and up and up. The red wiggles are the annual cycle. There's more land and plants in the northern hemisphere than the southern hemisphere, so there's photosynthesis varies during the year, and that's the wiggles. But the underlying trend, you can see the black curve is just going up and up and up, and that's what's happened over the last 60 years. And we know that this is due to human activity because we can date the carbon in the atmosphere, and the carbon is old. It's coming from fossil fuels. And another thing that we can do, this sounds a bit scary, but it's not at all scary, is measure the amount of oxygen in the atmosphere, and that's going down by a very tiny amount because of the combustion of the fossil fuels is using it up. That's nothing to worry about in itself, but it's a scientific signal. Now you see here we are in these units here of parts per million, so 400 parts per million. Again, that's the 0.04% I was mentioning before. And it started, this plot here, 320, and now up at 420. Now let's go much further back in the past and see what it was doing further back in the past. And this is concentrations over the past 800,000 years. That's a very long time. And here's the units again. So 400 is the top, and 320 is here. And this is what it's been doing over the past 800,000 years. And these measurements come from ice cores in the Antarctic and other places, in Greenland, where the air was trapped when the snow got laid down, and they can analyse the content of those air bubbles and deduce what the carbon dioxide was like in the air then. And you see it's going up and down, and I'll come back to the ups and downs later, but it's never been above about 300 over that period. And if you put the Hawaii measurements on top of that, I mean, it's so steep and so high, you can see we're not in a natural situation now. And indeed, CO2 is now higher than in 3 million years, so we can actually extend the CO2 measurements back in the past much further. And it's higher than it has been in 3 million years, when the continents were in different places and the land was completely different, so it's just a different world then. So it is entirely unnatural, this high value now, and it's due to human activity. So now some physics. I'm going to test those of you that are, especially those at school who are doing science at school. We're going to do the laws of physics applied to the atmosphere. So the first one. Oh, they've all gone now. Oh, I'm spoiling the story. Can you make it go back back quite a few, please? Oh, you're seeing all this talk in advance. Back. There. Right. So the first thing is Newton's second law. So I was going to ask you to tell me what Newton's second law is, but there we are. Force is mass times acceleration. And this is the forces acting on the air, was what's driving the wind. So number one force is gravity, and then you've got forces like the pressure gradient force. So if the pressure's higher over there than it is over here, the air will try and come over here. Then we've got things like the circulation of the Earth. Rotation of the Earth makes the air circulate. So we can put all of those into an equation, which is essentially representing the forces on the air. Then we have conservation of mass. You can see if you've got a parcel of air here and you've got some wind blowing through it, if the air comes in and doesn't go out, then the density will increase. Conservation of energy, so you've got the sun's radiation coming in and the heat radiation going out and what that does to the temperature. And then you've got the equation of state, so relating the different variables in particular. This is the ideal gas law. So we got 6 equations for 6 unknowns. There's 3 winds, because the wind can go north, south, east, west, or up and down. Then you've got pressure and density and temperature. You've got 6 unknowns and 6 equations, so that's like simultaneous equations. You can solve it. So you put it on, if I can do just one of these. I honestly only pressed it once. And I didn't press the black one. Perhaps, can I have the one without the pointer and use that, and then I won't have the pointer, but never mind. So you put all those equations on a grid representing the atmosphere. You see, this is an example of a grid, horizontal and vertical, and you've got the equations on every single of those grid points, and you can solve them, and you can look and see how it changes in time, and that's how you do weather forecasting and also climate modelling of the atmosphere. So it's very simple, fundamental physics being used to do these forecasting. I'm going to try and make it go forward again. No. All right, try again. Yes, so I've made the physics sound very simple. I mean, it is conceptually very simple.
Sorry, Joanna.
Yeah.
Please tell me this is better.
Thank you.
But still the lasers on the other one.
Oh, okay, thanks very much. Yeah. So I say, the physics seems okay. I've been making it sound really easy. It's basic physics. We can write down the equations, so very good. Why aren't weather forecasts perfect? I've made it sound so simple. So, of course, the thing is that the real world is a little bit more complicated than a little cuboid grid of values. And there's a number of different complications which we need to take account of. The first is the size of the grid. So, you know, the smaller you make the grid, the more detailed you can look at the weather patterns and things. And this is why the Met services are always asking for more and more expensive computers, because they want better and better resolution and more data and faster. Next thing is, you don't need to look at all this picture, but that's just to show that if we're going to try and represent clouds and rain, it's a lot of complex processes need to be included. And finally, and importantly, is something called initialization. So if you're going to step forward in time, you need to start somewhere. And you start from an initial data set, so you have to get an additional data set from somewhere. If you're doing weather forecasts, you use today's weather to forecast tomorrow's. And similarly, if you're doing climate modelling, you use the current situation to look at what's happening in the future. But of course, you need to initialize all those parameters at every grid point. And if something's slightly different, you can get a slightly different answer. And this is where the initialization data is really important. And this is an example of where the initialization data wasn't very good for a weather forecast. And I won't dwell on this, but the British Met Service didn't come out of it very well, let's say that. So, weather and climate. So I'm saying there's problems with the forecasting with this initialization. And you could ask, how can a computer model which has a limited success in forecasting the weather over 10 days have any hope at all of looking at the climate over hundreds of years? Perfectly valid question. And to understand that, you need to understand the difference between weather and climate. So weather is looking at what it is here and now in the short time. So we can say, what's the weather going to be in Madrid next Tuesday? That's a weather forecast. But if we're doing climate, we wouldn't ask that sort of question. We say, what's the general temperature in the centre of Spain going to be like in so many decades hence? And not only what is the average temperature, but also what is the spread of probabilities on that temperature. So the climate forecasts are not forecasting the same thing as the weather forecasts, but they are using the same physics. So back to this again. This is a key question. Can we explain the shape of this graph? And to do that, we have to include in our model simulations all these different variables. So on the right there, I've got a list of things that are included in the simulations. There's in the middle, the natural things, so solar radiation. Now, solar radiation varies through the year, obviously, and across latitudes, and across seasons, so we represent all of that. There's also some changes due to solar activity. You may have heard of the 11-year sunspot cycle and variations in the suns. Very small changes in the energy, but we need to take them into account. And then volcanoes. Volcanoes are actually very important because when they do a big eruption, they chuck a load of stuff up into the atmosphere, and that acts like a sort of cloud which reflects solar radiation back to space. So there's periods you can see here, perhaps. See the little spikes there and there. That's the temperature going down in response to big volcanic eruptions. So it has a global effect on temperature. So those are natural factors. Then we've also got to include the man-made factors. So I've talked about greenhouse gases, but I mentioned industrial pollution. If you put a load of particulates, smoke and SO2 and things out of industrial activities, that can act just like the volcanoes, reflecting the sunshine back to space, so that's important. And then land use, I mentioned changes in reflectivity. We also need to include the fact that the energy is going in and out of the oceans, so I'm not going to talk about that at all, but that's like part of the El Nino that you might have heard about. And then natural variability. It's a complex system. It's a lovely complex system, and mathematicians here may enjoy looking at complex systems, and this is one to end all others. So you need to include natural noise in the system. And then if we put all those things in, and we do the computer simulations, and the black curve there is the observed temperature change that I showed you before, the wiggle, 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 but up bit. And then there's two sets of calculations. The green one includes only the solar and volcanic effects, and the brown one includes everything. So you see, before about 1970, you couldn't say whether or not the human activities are having any effect on the temperature. But after that, the only way we can simulate that rise in temperature is through having the man-made forcings. So that's one of the reasons we know that climate change is due to human activity. There's other evidence, not just temperature, Arctic sea ice. So in the Arctic, the ice grows and shrinks during the year. It's got minimum area in summer, and people measure that area. And there's a graph there on the left of the Arctic summer sea ice extent declining. It varies during the year, and you can see the minimum in September. The dashed line is the lowest ever, which is 2012, which is that white area up there is the ice, and the red is the average extent. And you can see this year, 2022, is the blue curve, which of course is stopping after September, but it's not the lowest, but it's well down there. Other things, sea level rise. Now the sea ice, which I talked about in the previous slide, is floating on the surface. So if it melts, it doesn't change sea level because it's just like an ice cube in your drink, it just goes to the same level. But ice on land, so there's some ice on Greenland in that picture, or indeed on the Antarctic continent. If that melts and goes into the ocean, that causes the sea level to rise. So that's one reason. The other reason is if the climate warms, if the water gets warmer, it expands, and it can't go much sideways, so it's got to come upwards. So about half the current sea level rise is due to thermal expansion. And you can see in the middle there, global average sea level change over the last 100 years, and it's gone up about 20 centimetres and rising. So this is going back again over the 800 or 400,000 years. I mentioned before, and I showed you the CO2 plot before, and I said it was going up and down, and I didn't say why. Here's the temperature plot for the same period. It's also going up and down, and you can see that it's in synchronicity with the CO2 there. And we can also plot sea level rise. So in this plot, excuse me, the blue is the temperature as same as above, and the red is sea level, and you see again it's going up and down. And if we look at the range of those things, the CO2 has been going up and down by about 100 parts per million. We've talked about those before. Perhaps about 7 degrees. And this is between interglacial periods and icy periods, glacial periods. So when it's cold, there's less CO2 and the sea level's lower. So in terms of what's going on at the moment, you see we've got we've gone up 30 parts per million or more, 100 parts per million. We've gone up another 20 odd parts per million on that. We've gone up a degree already. We've only gone up 20 centimetres in sea level because it's all locked in the system. It's slow. It takes a long time to melt the ice and for it to come onto the sea level. So that's all built in the system now. We're not going to escape some of that sea level rise. So why did these cycles come about? Well, they're initiated by changes in the sun's orbit around the Earth. So sometimes you hear people say, oh, in the past, CO2's gone up and down, temperature's gone up and down. What are you lot talking about? It's all natural. Perfectly good question. But it depends why it's going up and down in the first place. So across there, the cycles are initiated by changes in the Earth's orbit around the sun. Make very slight changes in the amount of solar radiation that reaches the Earth, so it's getting colder and hotter. And as, say, the sun makes it go a little bit warmer, a load of greenhouse gases, particularly CO2, but also methane, get released from stores in ice and under the ocean, in clathrates and all sorts of places, and that releases these greenhouse gases into the atmosphere, and that makes the initial warming more, and then you've got an upward spike. And that's why the changes up there is like sharp up and then a slowdown. So the solar effect turns off, and gradually it all goes back to normal naturally over very long periods. Of course, what we've got at the moment is not caused by the sun, it's caused by human activity, and it's not turning off, and it's happening very fast. So that's just to say that the current speed of increase of temperature is about 10 times faster than any of those coming out of the glacial periods. So I've talked about global averages, but of course when we're experiencing weather, you don't experience a global or indeed an annual average. You experience what's happening here and now, and what's affecting you is the extremes in your area. And this is statistics of Northern Hemisphere temperature extremes. So it's showing the temperatures across the Northern Hemisphere, and you've got the mean value in the middle, and you've got some warmer and some are colder. Obviously, you've got a nice like Gaussian-looking distribution. And what we can, that's the average at the beginning of, I think it's 1950 to 1970. But what we can see is how that has shifted over time, I hope. So it'll take a bit of a while to get started. There's a little movie, I hope, coming up, which shows how that distribution has changed over time. Ta-da! I know it takes some time to get started. No? No, right. Oh, well, that's a shame because it's... Oh, yeah, hooray. So you can see in decades, and you can see the distribution, which of course is wiggly, and you can see it shifting to the right, which of course is this global or Northern Hemisphere warming. And by the time you get to 2000 to 2010, the peak is about, this is in 1 standard deviation, but the standard deviation is also equal about a temperature, centigrade. So it's about 1 degree warmer. But the important thing is that if you look at the extreme values, so for example, if we look over here, this is 3 standard deviations, or somewhere that's actually 3 degrees warmer than the average over the globe. But what that was doing back in the early times is, I mean, the chances of that happening are absolutely tiny. But now we get to these dates, the chances of it happening are now up here. So what that's saying is there's a lot more hot places than there are hotter, extremely hot places than there were. And of course, concomitantly with that, there's fewer cold places, and that might be a good thing for some people. But what that does mean that we can say, I'm not using that one, I'm using this one. Summer 2018, which you may remember a few years ago, or indeed recently, temperatures will be more normal by the time we get to mid-century. They won't be extreme at all. So looking at extreme events, this is a bit of, looks a complex plot, but it's not. It's actually, you may see it's a map of the world. There's North America, South America, Eurasia, Africa, and Indonesia, Australasia. And this comes from the Intergovernmental Panel on Climate Change, 6th assessment report. I'll tell you a bit more about that in a minute if I get time. And these are observed changes in hot extremes since the 1950s. And this is done a statistical analysis. And so where there's been an increase in hot extremes is shown in red. If there were any decreases, it would be shown in blue, but there weren't any. And the spots tell you how confident we are that it's due to human activity. So you can see over much of Europe, Asia, and North America, extreme North America, that it's been an increase in hot extremes, and we know it's due to human activity. Right, so that's talking about what's happened in the past. If we're going to look to the future, of course, it's difficult enough forecasting the weather, but we've also got to forecast human activity because we need to forecast CO2 levels and things. So various clever economists and people do these sort of assessments of what might happen, and they come up with these things that are called socio-economic pathways, and they decide that you know, people in the world are going to burn a lot of coal or not, or change their agricultural practices in certain ways. And so that there's these sort of different ideas what might happen. So the blue one down there is a very, very sustainable future. Everybody's not burning coal and behaving themselves for the environment and all the rest of it. And the 8.5 one there is really carrying on as we are and worse. So that's the temperature changes. So by 2100, we see the temperature on the worst ones by about 5 degrees. And we've managed with the bottom one to constrain the temperature to about 1.5 degrees by 2100. And this is looking at the temperatures over the globe. If you look at, that's the top, is when the surface is warmed by 1 degree, which is like at the moment. The observed changes are on the left and the simulated changes on the right. You see, most of the warming is actually at high latitudes and over the land, so it's not uniform over the globe. So if you're, say, for example, in North Africa, you're going to feel it a lot worse than if you're in middle of Africa or somewhere in like the UK. But in the north, at very high north latitudes, it's the most warming. So those are the observed and the simulated, which I'm just showing that to show that the simulations aren't bad, not perfect, but they're not bad. Then below, we've got what happens at 1.5 degrees, 2 degrees, and 4 degrees. And of course, it's just getting gradually worse. Even at 2 degrees, most of the land is warmed up by more than 2 degrees. So if you look over Europe, it's about 3 or 4 degrees. And it's just the oceans where it's constrained to below. That value, which is seen by biologists and economists to be a critical value above which we mustn't go because of dangerous effects start taking place. You may think dangerous effects are already taking place if you look at, for example, the floods in Pakistan and things like that. This is looking at the annual average rainfall predicted. And I'm not going to talk about this in detail, except to say, of course, it's not warmer, it's not drier everywhere or wetter everywhere. It's some places different to others. So if you look in the Mediterranean, it's a lot drier. If you look over Southern Asia, it's a lot wetter in the monsoons and things. So depending on where you are in the globe, you get different rainfall effects. And this is the same thing for the heavy precipitation as I showed you for the temperature. This is heavy rainfall events, not just average rainfall. Much more difficult to do with the models than it is, this is observed, so it's not models. But the analysis, the data is not so good, so it's more difficult to do than temperature. But you see there's nowhere where heavy precipitation has decreased. Wherever there's any signal, it's increased. But the sort of confidence in human contribution is much less. Seems to be Northern Europe, where we've got the most increases in heavy precipitation that we understand. I'm going to skip that one. This is just a sort of almost a throwaway slide to tell you all the other awful things that can happen, which I haven't got time to go into. The actual human impacts of some of these things. So these are assessed what can happen. So 2 billion people with less water. 90 million people per year affected by flooding. So there's the dry, there's the too dry, and the too wet. Effects on plants and agriculture. And then exposures to heat waves, of course, is very bad health. I'll skip that one. Okay, it won't go away. It's just about the UK, but the point is, the middle column there, expected changes by mid-century. The average temperature is going up, hot summers go right up, summer rainfalls go down, winter rainfall goes up, and heavy rainfall goes right up, and sea level rise. So you can do these analyses for different parts of the world. Now, this is an important plot. What it's showing is the black friendly temperature curve that we've seen a number of times now, in degrees C, and then the cumulative CO2 emissions since 1850. So we put CO2 into the atmosphere, and it accumulates. So at any particular date, you can say how much has accumulated in the atmosphere. And because it's got very long lifetimes, so at least 200 years, it's sort of staying there. So the more the CO2 accumulates, and these, of course, are forecasts in the colours, the more the temperature goes up. And the different colours there are those different socio-economic pathways. So the worst one, which is the pink one, goes up a lot, which is what you'd expect. But the point of this slide is to show that whichever curve you're going up, the slopes are the same. So it's not really dependent on the rate, it's just dependent on the accumulated CO2, how much the temperature will be, which makes it a very easy conclusion from this figure. If you want to stop the temperature going up by more than 1.5 or 2 degrees, there's a budget of CO2 which you can afford to emit into the atmosphere. And after that, you've got to stop, because that's what this is about. So to constrain global temperatures to any value, you might think, oh, I don't care if it goes up by 3 degrees or even 5 degrees if you want. But if you don't stop CO2 emissions, it will just carry on going up and up and up, and it'll go through the 5 degrees, it'll carry on going up and up and up. So stop emitting CO2 and other greenhouse gases, and the sooner we do it, I think I've got this now, the sooner we do it, the better, and the greater the current emissions, the sooner you need to stop. It's a very, very simple scientific argument to make and also to understand. So this is about net zero, which you may have heard of. If any emissions continue, then greenhouse gases need to be removed from the atmosphere at the same rate as they're put in. And so some greenhouse gases, and particularly some like methane and nitrous oxide, it may be very difficult to stop emitting them because they, for example, methane comes out of a lot of agricultural processes. And again, nitrous oxide is related to a number of biological processes, so it may be difficult to get those to absolute zero in their own rights. So if you want net zero greenhouse gases, you've got to start taking CO2 out, emitting less CO2, or actually extracting it from the atmosphere. And there's a lot of work now being done on carbon sequestration from the atmosphere, how to remove carbon from the atmosphere, with ideas like sucking it out and putting it under rocks where oil has been extracted in the past, and all this sort of business, or how to solidify it. And it's a load of science really important. So I said I'd say something a little bit about the politics and what's happening. So the Intergovernmental Panel on the Climate Change, IPCC, was set up by the World Meteorological Organization and the United Nations back in 1988 to assess the state of the climate. And also the United Nations, sorry, it's all dreadful acronyms, but you get used to them after a while. United Nations Framework Convention on Climate Change, UNFCCC, was established in 1992. That's an international legal agreement to do something about it. And the UNFCCC has an annual conference of the parties. Now, the parties are the different countries, 198 countries that are members of the UNFCCC. And they have annual meetings. The first one was in Berlin in 1995. And they have them every year, but some of them are bigger meetings than others. And I've listed the bigger ones down there on the left. An important one was the Kyoto meeting in 1997, which agreed that countries would try and do something about limiting greenhouse gas emissions. In 2009, there was COP15, where those of us who were there were really hopeful that something was going to be agreed. Nothing was agreed. It was such a disappointment, really, really bad. Very, very disappointing. So when we got to 2015 and it was a Paris meeting, these are the big meetings. There's little meetings take place in between, but these are the ones where you're really expecting something to happen. We were just saying, please agree something. And the Paris meeting was quite remarkable in that they got unanimous agreement of the 197 countries, whatever it was, to try and keep global average temperatures below 2 degrees and make an effort to keep them below 1.5 degrees. And the difference between 1.5 and 2 degrees is actually very important to low-lying island states, so islands in the Indian Ocean and things which will actually be submerged if it goes above 1.5 degrees. Well, they're being submerged already, but they have to move away. Then we had the Glasgow meeting. I'll show you a graph of the results out of that in a minute. And this year we got a meeting in Egypt, which is not one of the big ones, but again, it's important that countries talk about something important. So what we got here is global greenhouse gas emissions as a function of time. And the green one there is what the models are showing must be done if we're going to keep temperatures to below 1.5 degrees. So essentially, they've got to, the emissions have got to peak now. They've got to get to half where they are now by 2030, and they've got to get to pretty much zero by the end of the century. That's what needs to happen. What was happening before the Glasgow meeting was the shaded blue at the top. See, there's some decline in terms of what countries said they would do, but it's going up to over 2.5 degrees global warming. And then there's the 3 lines in the middle. They're all different outcomes from the Glasgow meeting, different aspects that might happen. But you see, they're all, in 2030, still way up there. And this has become known as the emissions gap. So there's a gap between what we're doing and what needs to be done to get the temperature to below 1.5 degrees. So we're really missing the targets at the moment. So we need the emissions to come down. If you want to see, Climate Action Tracker is a good website which is showing what each of the countries is doing at any one time and what effect it's having. Well, I'm not going to go through this in detail. This is what can we hope for from Egypt. The discussions are largely on money, because the poor countries obviously need financial support, both to help them not emit greenhouse gases, but also to adapt to the changes that are coming out as a result of all the rich countries burning fossil fuels. And I think I'm just going to, that's the end of the talk. I'll just leave that up. 9 things you can do about climate change. Thank you very much.
Thank you very much, Joanna. I think there's a lot more we know about the science of climate, no, and how things are measured and how they are modeled and what we know. So, okay, so the floor is open for questions and any issue that you may have with climate. This is probably one of your best opportunities to ask. Yeah.
So, sorry, I have a bit of a sore throat. So I was just wondering, when you showed us the maps about the temperature mean across the globe, you showed that in the poles the temperature is going to get, the mean is going to get higher than in the equator and other parts. What is the cause of this event?
So it's largely due to the fact that there's ice at the poles, and the ice reflects sunshine back to space, which makes the poles colder than they would be were the ice not there. As you melt the ice, there's less reflection, and it gets warmer. So it's called the ice albedo effect, if you want to know. It's been observed as well as theoretical. Thank you. Very clever question.
Thank you.
Very much for your presentation. It was quite enlightening. My question goes with you show the periodic change of the carbon dioxide content and the temperature in the previous past, the glacial ages.
Yeah.
And you explained clearly the mechanism, that the origin was the changes in the overall radiation that came into the Earth. And then that causes, this is a non-linear effect that it really means, and then the carbon dioxide and all the rest of greenhouse gases rise. But why is the mechanism why they relax again? You showed clearly that the relaxation is much lower, but I missed the mechanism of why the climate system gets to what would be normal.
So the initial effect is due to the, I think it's due to the tilt of the axis of the Earth. Astronomers and people around here probably know better than me, but varies on timescales of 100,000 years. And that gives the initial push. And then there's this positive feedback effect that you described, thank you very much, very well, What happens when it starts going back again is, of course, that the CO2 and other gases have to get reabsorbed into the stores from which they have been released, which is a much slower process. You know, you can imagine if you heat up something that's going to release the CO2, but if you cool it down, it takes a while for the CO2 to get reabsorbed back into it again. So that's why the decline is on much less steep than the increase.
Yeah, but my question is, why it not keeps rising infinitely? I mean, there might be something that changed in the...
Oh, yes. So the tilt of the orbit, whatever the parameter is, and I'm sorry, I can't quite remember which it is. It might be a combination of the tilt and the ellipticity of the orbit. They go back. You know, they have 30,000 and 100,000 year timescales. So you might expect the whole thing to be sort of harmonic and sinusoidal, but it's not because of these feedbacks.
Okay. So basically that the causes, the original causes disappear and then the system returns to
Yes, exactly. Yeah.
Thank you very much.
Thank you.
Hello. Is there any way to remove the carbon dioxide from the atmosphere?
Well, there's a lot of work on this now, and there's several ways that have been proposed. You can have chemical effects and things that are artificial trees, which are somehow or other got some chemicals. You chemists will tell me what, that can absorb the CO2 and then it gets stored. Or you can actually suck the CO2 out of emissions from power stations as it's released, suck it out and again solidify it or liquefy it and put it in some store. There's all sorts of clever things people are doing, like growing plants that are especially good at absorbing CO2. There's lots of imaginative ideas. The trouble is with all of these things, well, there's two problems actually, two main problems. One is that somehow or other you've got to store the stuff forever. You can't just take it out the atmosphere and then say, okay, you've got to store it. The other thing is that at the moment, the ideas are incredibly expensive and there's no financial incentive on anybody to do it. You know, the obvious thing, and sorry to make a political statement, but the obvious thing would be to make the oil companies be responsible for sucking it out of the atmosphere. But at the moment they're not. Their profits are entirely dependent on how much coal and oil and whatever they can sell. So there needs to be a financial incentive as well as sort of physical engineering solution. There's one in the middle on the left. Mm-hmm. Yeah.
What's the reason behind the North Atlantic anomaly?
Now when you say North Atlantic anomaly, do you mean that the fact where it's not actually cooling in the north? Yes, that's really interesting. And the oceanographers are very keen on this. So he's very observant. He's noticed that in the plots of the global distribution of temperature, where everywhere was warming, some places are warming more than others, but in the middle of the Atlantic, it's actually cooling. And I think the answer is not entirely certain, but it's probably due to changes in the overturning circulation of the ocean. So as cold water comes up from below, obviously that creates a colder patch. If you change the speed of the overturning circulation in the ocean, you get different patches of temperature change on the sea surface. I'm sorry, that's a vague reply, but you get the idea. And oceanographers are, of course, very excited by this and doing a lot of computer modeling and trying to reproduce the effects.
Hi. My question was, when you were talking about the different things that affect the rise of the temperature, you were talking about the natural physical effects and also the man-made ones, but you also mentioned the noise, the complex system.
Yes.
I was wondering if you could further develop on it.
Yes. So again, for mathematicians, this is really an interesting topic. And it's it's slightly related to this ocean issue. You may have heard of the El Niño Southern Oscillation, where the temperatures in the Pacific go up and down on about a 4-year timescale, and that's one example of a natural fluctuation in temperatures, which is brought about by an interaction between the sea surface temperatures and the atmosphere. But there's also natural variability where it's just going up and down. I mean, you know, if you've got a bucket of water and you slop it around, it's doing this. And we've got a great big bucket of air and water and stuff. So it's just natural variability. And when we do any of the studies, we have to accept that that's going to be a band of uncertainty of our results. Now, as scientists, when we talk about uncertainty, you know, you who do science will know that uncertainty, you have to, when you're doing your physics experiments, you blooming well better do the uncertainty range or else you get into trouble. But we have to do uncertainty. People who are not scientists think that if you say you're uncertain, then you don't know what you're talking about. So it's a bit of a problem with a label. But yes, so the uncertainty bounds are dictated largely by the natural variability or the noise in the system.
Thank you.
Hi, thank you.
It's on. It's on.
Hi, thank you very much for your presentation. That was amazingly interesting. I was wondering about the discrepancy between the simulation and the actual data regarding the 2 poles. We can see that the agreement is very good in the North Pole, but not so good in the South one.
Yes, and there's a big question about ice and what the ice is doing. And so it's not just a question of temperature, it's the latent heat of the ice melting. And I think what the ice physicists are looking at now is if you've got an ice shelf like this and it's getting eaten away underneath by water and the water's getting warmer, what that does to the ice shelf. And that changes, obviously, the area and thickness of the ice shelf, which affects the albedo of the radiation and also the amount of fresh water that's getting melted into this. So it's an area of active current research. Lots of interesting physics, but you're right, it's not very well known.
Thanks for the very interesting talk. It's good to remind something which is not the next funding project and so on for next Monday. I had a question about what's the status of our understanding of the tipping points in the climate system?
Yes. So he's asking about tipping points. Now, tipping points is the name given to something where it's a nonlinear effect that sort of takes over. So one example given is if you start melting permafrost in the northern hemisphere, it releases methane, which of course is a very strong greenhouse gas. If you release the methane, it gets warmer, which melts more permafrost, and it can get, the idea is, the tipping point is that it's a runaway effect and you can't get back to where you were. And there's other examples of tipping points. One is called Amazon rainforest dieback, where you get rid of so much of the trees that they can't actually create the water in the natural ecosystem to keep the Amazon going. There's others, one related to the overturning circulation of the North Atlantic Ocean, whereby, anybody seen the film The Day After Tomorrow? Ever so funny. not exactly realistic, but it starts off with, anyway, the scientists getting confused because it's getting very cold. The idea there is that the North Atlantic only overturning circulation has stopped. So you're not getting the warm water coming to the northern hemisphere, coming from the equator to the poles as it is. That's another tipping point. I'm trying to think of other ones. There's other biological ones and things. I can't remember what they are. I think in terms of if any of them are actually happening, many of these processes are happening, but at the moment it doesn't look like we're heading for any real tipping points. That's as far as I understand it, which is good news. But of course the bad news is that if we don't do something about it soon, then we will be getting to the tipping points. Yeah.
Okay, thank you very much for your talk, really very interesting. But I would like to talk about the theoretical models. When you have a system is open system, you have a nonlinear system, and you have initial conditions. Everybody knows this is a chaotic behavior, a chaotic system. You mentioned initialization, okay? But in what extent the projection you have, or you are able to get, you have to correct in somehow the chaotic behavior. Because in principle, your model has to be chaotic, completely chaotic.
Yeah.
Which is are we confident with these theoretical models?
So the question concerns uncertainties in forecasts if you're based in an uncertain ergodic sort of model and system indeed. So if you're looking at weather forecasts, now one of the best weather forecasting units in the world is the European Centre for Medium Range Forecasts, situated in Reading in the UK. And they're doing what they call medium range weather forecasts, which is up to, say, 10 days ahead. And what they do is they have an ensemble of forecasts. So they start with a certain set of initial data, they do their forecast, then they start with another set, do another forecast. And I can't remember how many they're doing now, but it's something like 30, an ensemble of 30 different simulations. And then they get a spread, obviously a spread in the results. And they usually use for the forecast the average of the spread, but sometimes they see a bifurcation. So there's something going off in this direction, something doing something completely different. And sometimes they'll actually give you two forecasts. And they'll say, we don't actually know whether it's going to do that or that, which I think represents what you're talking about. That's the weather.
That means you are controlling the chaos behavior?
Sorry?
You are controlling the chaotic behavior in a certain sense?
No? I don't understand the question.
If you are controlling the chaotic behavior of the system?
No, not at all.
Okay.
No.
Because when you change initial conditions, you know the chaotic behavior can go there and can go there.
Yes.
Okay? There is no rule you can, or you can forecast something for sure.
No, it is a naturally chaotic situation,
Yeah,
and the only way that you can look at it is by allowing it to be chaotic. I mean, that's what it, assuming the models are anything like reality. And seeing what the probabilities of certain results are. And we do the same with the climate models as the weather forecast for 10 days, but for the climate forecast for 100 years, you know, again, you look at the spread.
Hi, thank you very much for your presentation. You said that with the volcanic eruptions, the temperature decreases a little bit, but is the fact that after a volcanic eruption, everything around the volcano is covered by black rock and acid? Yes. Is that important for? Because I think that this type of black material absorbs the sun energy. Or
well, you're absolutely right. And in local terms, of course, that change in the local landscape will affect the local weather and climate. But if we're looking for global effects, that will be quite small. The dust from a volcano, if it gets up into the stratosphere, it goes right the way around the globe, and it stays up there for perhaps 2 years, and then it becomes a global effect. Whereas your effect is very much a local effect. That's not to say it's not happening. And in terms of the local weather, you'd need to take account of the local reflectivity of the ground, and that would be important. Yeah.
Okay, thank you so much.
Thank you very much for your fantastic talk. What is your outlook on electric vehicles? Do you think that's a reasonable, or is just to make us feel that we're doing something?
Well, they do make us feel that we're doing something, but I think they are doing something in two ways. One is they certainly reduce fossil fuel consumption, and the second thing is they get people into a certain mindset where they start thinking about it, whereas they didn't think about it before, and especially if governments put some sort of taxes on dirty vehicles and encourage the purchase of... Of course, they're not perfect, electric vehicles, and one of the big issues now is batteries, and how you create the batteries and where you source the chemicals needed to produce the batteries. But then there's people working on hydrogen fuel cells and all sorts of things, a wonderful scientific endeavours and innovations. So I certainly think they're a good thing. I mean, I've got one, so I have to say that.
Thank you very much.
Hello, good morning. I was wondering about, of course, it's negligent to have an aeolic system, a wind turbine, but now that every country is installing huge quantities of surface, how is going to affect to all the models wind speed, at least in the lower strates of the atmosphere?
That's a good question. I don't know the answer. There is work going on the influence. The question is about whether wind turbines affect the local meteorology, especially where you've got very large areas. And there is some suggestion that they can affect the wind downstream, say a few kilometres. But whether or not that's harmful or not, I think is still an open question. There's also people who are concerned about the effect of wind turbines on birds and the natural world, and under the water, whether the building of these great big things is actually affecting the underwater life. So these are all issues that need to be considered seriously. But at the moment, I can say from a UK perspective, offshore and onshore wind is really the way that we can see of solving our fossil fuel dependency.
More questions? Yeah, there's one at the back.
Wonderful presentation, really. I had a question. In one of the slides, you showed that Spain and Portugal and this region would get a lot drier in result of climate change. How extreme could this effect become in the long-term future?
The drying?
Yeah.
Of Portugal, did you say?
Yeah, of Portugal and Spain.
Yes. So I haven't got any more information than what was shown on those slides, but you can see that the rainfall is going down and the potential for drought is going up, and that will just go on getting worse.
Okay, thank you.
That was a very enumerate answer.
Hello. Yeah. Hey. Yeah. Yeah.
Oh, hi.
It's maybe a simple question, but thanks for your talk first. And is there any initiative to increase the albedo effect?
Oh, yes. Well, now he's asking if there's any effort to increase albedo. So that gets us into the whole territory of what has become known as geoengineering. And you better not get me started on geoengineering, because particularly albedo geoengineering, I think is, to put it crudely, completely batty. That means stupid. But some ideas are more sensible than others. Let's start on some of the less sensible ones. Giant parasols in space, huge, great reflectors. This is not just science fiction. People in American laboratories are working on the sort of reflectors that you'd need and how much fuel you would need for the rockets to get them up there and keep replacing them. More sensible one, paint your roof white. Well, that's okay. If everybody paints their roof white, maybe that will make a bit of difference. Growing plants that have got more reflective leaves. That's another one. Boats which suck spray suck water out of the ocean and make very lots of small droplets, which is like a reflective cloud. I can't remember the number. There's so many different ideas. But, I mean, maybe some of them might work a bit in practice. I think the main problem with all of these things is that they give people an excuse not to address the real problem, which is the emission of greenhouse gases. So they think they can do the emission of greenhouse gases and then they can do this geoengineering stuff. Oh, it'll all be all right. I mean, yes. These things don't correct the original problem. Even if they did the energy balance right, they're not doing the wavelengths the same, so it wouldn't be it wouldn't be correct across the globe, and it wouldn't be, you know, oh, yeah.
Can you hear me? Okay.
Hello.
Thank you for the talk. I just was wondering, how do we get the temperature values that we are based all our hypotheses on? I mean, from which kind of devices, or how are them distributed along the planet? Or
yes, that's a very important question. Of course, is how do we get these global temperature measurements, and what measures them, and how accurate are they? So if you go back to about after 1850, there are scientific measurements with thermometers, and people have taken them at different places in the world. Obviously, there's been more of them in the places like Europe, where they've had science laboratories and things, and fewer of them in places like Africa. But there is a lot of attention paid to assessing individual records, how accurate they are, how much they contradict or otherwise other temperatures in the same area. And in constructing the temperature maps is a huge job, and it takes people all their careers to do it. I mean, the one I know about best is the one at the University of East Anglia, but there are other places around the world doing it. So that with the 6 different colours that I showed you of the lines right at the beginning, that's different people's assessments of what the temperature's doing. If you go back before, when we had scientific measurements of temperature, we have to use things which are called proxies, so that they are measurements of other things which indicate what the temperature was. One that's talked about a lot is tree rings. So the growth of trees depends on the temperature each year, and if you look at the tree rings, if you know about it, you can deduce the temperature. There's all sorts of complications to do with that as well, of course, because they depend not only on temperature but also on humidity and other things too. But again, there's a lot of work being done on tree rings. There's ocean sediments. You can see signals of temperature deep in ocean sediments, and lake levels is another one. So there's a lot of science goes on into trying to reconstruct these temperatures. Very difficult.
Thank you.
Hi. Here. Here. Thank you for your talk. I would like to ask you if you could tell us something more about your personal journey when it comes to the science of climate change. Like, how did you get started and get into this world of science?
So the question concerns my career and how I got into this stuff. As a kid, I was a bit of an old science geek, you know. So I actually had my own weather station in my garden, which wasn't very accurate, but I had my dad's backsmin thermometer, and I built my own rain gauge with a funnel, and I calibrated it and all this sort of things. I know you're sighing, you're thinking, how sad. But anyway, that's what I enjoyed doing. And I was good at science at school. So when I studied physics at university, and to be quite honest, I'm sorry to physics academics here, I thought it was a bit boring. I mean, it wasn't really, none of it was very exciting. So when I stopped my physics degree, I thought, what am I going to do next? And I had a gap year, and I spent the gap year traveling with my now husband mainly around the Mediterranean, Turkey, and the Middle East. He's a historian, he wanted to look at archaeological sites. But while we were doing that, I was looking at the weather and the climate, and there were so many fantastic things going on, the sunrises, the storms, and I thought, this is definitely what I want to do, is meteorology. So I did a master's degree in meteorology, and then I went back to a physics department and did a doctorate in atmospheric physics, which was incredibly dry. It was all to do with the spectra of the gases and what happens. But you see, when you know why you're doing something, when there's a reason for it, I'm talking about myself, of course, when you know why you're doing it and there's a reason for doing it, it's much more interesting than when you're just learning it out of a textbook. So, yeah, I got involved in theoretical atmospheric physics, and I was doing that for some time, and theoretical climate change without really feeling it somehow. But then when it got to, 20 years ago, sort of thinking, hang on a minute, it may have more important things. I was distracted by being head of the physics department at Imperial for 5 years, which certainly didn't leave you much time for thinking about the weather, and dealing with all those naughty physicists who weren't doing what they were told. But after that, I joined the Climate Change Institute, and that was where I really felt it could make a difference, not just in talking about climate change, but encouraging people to work on different aspects of it. And we need to do that more and more. So I hope you will.
There's another question there. So, any more questions after this personal one? Yeah.
Oh, I thought I'd escaped.
Thanks. So I would like to know how much change should be experienced in the Earth conditions for it to be inevitable for humans.
Yes. So as I say, the economists and the social scientists and the biologists and the agrarians and all the rest of it thought that 2 degrees seemed to be a global average, seemed to be where that was the limit of safe temperature rise. But then you have as I say, the low-lying island states think that they're going to be in a bad way after 1.5 degrees. And actually, when we get more into looking at the geographical variations and the changes in extreme weather, even 1.5 degrees looks like a problem. And it's not just changes in the weather, it changes in things like corals and things. If you get just above 1.5 degrees, the corals will start dying off. So really, it's quite urgent.
Thanks.
Hello.
Hi.
Thank you for your talk. I kept thinking about this graph you showed us about like where it got like really rainy and where it got very dry. And it didn't really make much sense to me because what is actually happening? Can you see like 2 meters away it's raining a lot and then on your side it's not raining at all? I mean, won't there be like any wind to move the clouds from side to side? I don't know.
Not 2 meters, no. But of course, if you look at the weather maps now, you'll see like low pressure systems coming across the Atlantic. And you know, in the middle of the low pressure system, it will be raining, and in the high pressure system behind, it'll be drier in general. So if you change the positions of those low and high weather patterns, you can completely change the local meteorology without actually a huge change in the system. So I don't know what's the determining factors of the weather in Madrid, but certainly on the west coast of Spain, the rainfall there will depend entirely on where the shifts in the jet stream are going.
Thank you.
Okay, okay, maybe the last question. It's clear that the subject is of interest.
Yeah. Hello. What are your thoughts about the hydrogen combustion and hydrogen-powered vehicles? Like, you feel like maybe it is like a possible alternative to the combustion of fossil fuels, or that's it?
So again, this is another solution that's definitely a lot of people working on it. So the idea is if you burn hydrogen, the only waste gas is water vapor, so there's no problem with CO2 and things. The real issue is where you get the hydrogen from. So there's essentially two, at the moment there seem to be two ways of doing it. One is called blue hydrogen and one is called green hydrogen. With the blue hydrogen, you create the hydrogen by whatever you need to do, splitting water or something, but you get the energy from fossil fuels or somewhere else, which makes the whole thing far less green than it should be. The green hydrogen, you're getting the energy to do the water splitting from wind or renewables or something like that. And I think both of these are being worked on, and they certainly work, but the question is, will they work at scale and at a sufficiently low cost to make them generally applicable? I mean, water vapor as a waste gas is absolutely fine, and as I say, it's controlled by its temperature, so it's not a problem. But it's down to the engineers now, really, to see if they can sort it out.
Okay, thank you very much. If there's somebody else with a pressing question, then please come down after the session. Okay, the really urgent one.
Yeah, sorry. It's just, well, I wanted to ask you if you think like it's actually possible to revert like this climate change. Like, I mean, it's a good idea to like cut the CO2 emissions, but is it like something realistic?
I don't think it's realistic to expect a reversal. I think the best that we can hope for is to slow down at the moment, unless something really changes in terms of the engineering. Yeah.
Okay, let's thank Joanna again for this really interesting talk. Thank you. The Curie Colloquium will be back with us in December. We'll be in touch. I think we hope you can come again. Thank you, Elisa, for bringing so many young people. Thanks, Anna, for coming. Thanks to all of you for being here. I hope you enjoyed it.